Now that we've found the R square based on sums of squares due to regression and the sums of squares total, and we've found the coefficients that produce our predicted regression line, we want to see whether we are actually predicting anything with our regression line. What this means is whether we are explaining a large enough proportion of the variance in total charges to say that we are actually predicting something. It's also the same as asking the question whether our coefficient B1 is actually different from 0. The coefficient B1 here at $803 is quite large. We would almost automatically say, yes, that must be different from 0. But the question of whether it's different from 0 has to be answered in relation to its standard error. And that answer is essentially a t-test that we've already looked at. So let's move ahead to address the question of whether we're predicting a significant proportion of the R square and whether the coefficient on B1 is actually different from 0. The first step in answering these two questions will be to generate an f-test. The f-test will be a test of whether the sums of squares due to regression is large relative to the sums of squares due to error. But we will not actually use the sums of squares in either case. As was true in analysis of variance, we will use the mean square due to regression, which is the sums of squares divided by the appropriate degrees of freedom, and we will use the mean square error, which is again the sums of squares error divided by appropriate degrees of freedom. In any simple linear regression, there is 1 degree of freedom in the sums of squares due to regression. This is because we are using one predictor, in this case length of stay, to predict the regression line. So the mean square due to regression will be simply equal to the sums of squares due to regression divided by that 1 degree of freedom. Again, in simple linear regression, there is always n minus 2 degrees of freedom in the error. The total sums of squares has n minus 1 degree of freedom, and we take out an additional 1 degree of freedom for the regression line. So the mean square error is equal to the sums of squares due to error divided by n minus 2. In this case, n is 20, so 20 minus 2 will be 18. And the sums of squares error is approximately 964,000. Now the f-test of whether we are accounting for a significant proportion of the variance in the R square is equal to the mean square due to regression divided by the mean square error, and the f value is 63.33. This f value is really large enough that we could immediately reject the null hypothesis of independence between total charges and length of stay, but we can find the actual probability of that f with f dist, the f value, degrees of freedom in the numerator, which is 1, and degrees of freedom in the denominator, which is 18. And we have 2.639 e to the minus 07 as the probability. This is a very small number. And on the basis of that probability, we will reject the implicit null hypothesis that total charges is independent of length of stay. Let's take this one more step and look at the t-test that will determine whether $803 is different from 0. The first thing we need is the standard error of the regression. And the standard error of the regression is equal to the square root of the mean square error, or $982. That is the standard error of the regression line itself. The standard error of B1 is a little more complicated than the standard error of regression. It is actually the standard error of regression divided by the square root of the sums of squares in x. That is, the square root of the sums of the squares of x minus x bar. So here we will say that this is equal to the standard error divided by the square root of the sum of squares of x minus x bar, and the result is 101.0235. Now the t-test is essentially just the value of the coefficient B1 divided by its standard error. So here we have t is equal to 803 divided by 101, or 7.96. One of the characteristics of this t value is that in the case of simple linear regression, it is the square root of the f value. To see that, I will put right here the square root of the f. Exactly the same value. The probability of the t is also exactly the same as the probability of the f. It is equal to t dist, the t value, the degrees of freedom in the error, and this is a two-tailed test. In regression analysis, the test for the coefficient is always a two-tailed test. When I hit enter, we can see that this value, this probability, and this probability are exactly the same.